Okay, so do you have any questions first?
Suppose we have a wire, it carries a current out to the upward direction. Then we are rotating the wire with two different rotation.
Okay, so you have this current I. Okay, then you are rotating the current. Okay, nothing changes.
Yeah. The current doesn't change or change?
No, it doesn't change.
One, the speed of changes. Speed of the moving charges.
So how do you rotate? I mean, you have this wire, you are rotating it like this. Well, ideally the wire is a point out, has a zero thickness. So its rotational speed is zero.
Better than, let's say, real wire. Better than.
Of course. Yeah, they will have some circular motion. They will also do some circular motion. They might, let's say. Now, because you see, how do you rotate them? You rotate the wire, but how do you rotate the charges inside the wire? How do you exert force? How do you exert a torque on the charges?
Does the wire exert torque on the charges?
I mean, if it is homogeneous and perfectly symmetrical, no. There's nothing to exert a torque.
Second question is, we rotate the wire. I say, current this one, and we rotate this one.
Okay.
Then we may get zero current, right?
What do you mean zero current?
Charges moves, doesn't move.
Due to the rotational motion. Well, I mean, how much should you rotate it?
Yeah, the question. Yeah, it can be the question. How much should I rotate it?
I mean, assuming you can even rotate at the speed of light, well, eventually everything will break down, sure. So?
Other speed? In other speeds, is it possible?
I mean, I would say you should really rotate it very fast. You see, there will be other more important effects. For example, you will be changing the magnetic field and in creating additional electric fields. That electric field will modify your current.
So getting zero current is almost impossible.
I mean, it might be possible, I don't know. You have to work it out. You see, let's look at some other example, whether not the rotation itself, but even the system itself creates some additional current, additional EMF. You have your cylinder, and wrapped around it you have your wire. We had already seen that if, let's say, the current is let's say the current is running in this direction, so the B field is upward and uniform. We had already studied this system. This is I. And then, let's say here, the current is running in this sense. If you just look at it from the top, there will be an upward B field, uniformly distributed. In the solenoid. And suppose you try to increase the current. Well, how you do it, you have a battery, you just increase the voltage of the battery. You add another battery, etc. You try to increase the current. Now, what will be the direction of the induced electric field? It will be clockwise. Well, it will be clockwise and it will be everywhere, including on the wire. Well, if there is an electric field on the wire in the opposite direction of the current, you have to push harder to create the current, to increase the current. So you have to be doing additional work. If you want to change the current somehow, the system will resist it because of the magnetic effects. Similar magnetic effects will also happen if you take a wire, you rotate the wire. the system will resist the change. Or let's say if you want to induce EMF will resist change. Let's look at the other two. Case 2, di by dt, you try to reduce the current. So what will be the direction of the induced EMF? Counterclockwise this time, not clockwise. So the induced EMF will be in the opposite direction. So that is, the induced EMF will be in the direction of the current. So it will try to increase the current, existing current. This time induced EMF will push the current, will still resist change. Now, if you take a wire, if you try to rotate it, well, same thing happens. This effect will probably be more important than any mechanical effect that you can create by rotating. The more important thing will be this induced effect. I don't know it for sure. You have to just work out the details, but at least this is my intuition, let's say. Okay, so any other questions?
Instead of rotating sphere, if we had rotating electrode, what would happen?
Well, the calculation will get much more complicated, that is one thing. But the basic idea is the same. Conceptually, nothing really will change. No new phenomena. Just, it will be technically more complicated to calculate. Of course, if you have an ellipsoid, it won't be an electrostatic system this time. Sorry, magnetostatic system, it will be magnetodynamics. Of course, assuming, okay, so if you have such an ellipsoid whose cross-section is a circle and you are rotating around an axis that is perpendicular to this circular cross-section, again, it's a magnetostatic system, nothing will change. If you have an elongated ellipse in the, let's say, x or xy plane, it's elongated in the xy plane, and you are rotating around the z-axis, in that case, it's no longer an electrostatic, magnetostatic problem. So you have to do the magnetodynamics, electrodynamics, etc. So it will start radiating. That hopefully we will study next week. In the remaining 2 weeks, let's say. So there are basically two things I would like to discuss. One is the light, and the other one is radiation. How do we radiate light? Now let's go back to our example that we were discussing on Wednesday. If you remember that example, we had this solenoid which was carrying, let's say, a current in this direction. And so there's a uniform outward magnetic field. Whose magnitude was, what's the magnitude of this magnetic field? No, there is no 2 pi r. You see, to calculate this B field, what we can do is this: if this is our solenoid, just take such a loop, and around this loop, B dot dl should be equal to, around the loop, it should be 4 pi over c times I enclosed. The induced EMF will have this 2 pi r factor. So this was our B, and then we imagine that we put another cylinder inside, with a surface charge density plus sigma, which created an additional electric field in our system. There is additional uniform electric field. Well, we have this region, let's say this radius A, the outer cylinder has radius R. In the region between the inner cylinder and the outer cylinder, we have the E and the B fields, both of them. So the pointing vector, which was C over 4 pi, E cross, well, we are looking in vacuum. E cross B is non-zero inside our solenoid. And the electric field created by this system had the magnitude. Let's say this has that 1 over 2 pi s, let's say 2 pi s being the distance, and the charge will be 2 pi a sigma. So this would be the electric field. A sigma over s. This is in the s hat direction. B is 4 pi over c I over n in the z hat direction. So the pointing vector is c over 4 pi a sigma over s hat cross 4 pi over c I n. In the z hat direction, 4 pi over c is cancelled, and we end up having a sigma I n over s. Well, s hat cross z hat is minus phi hat.
Is the s between r and n? S between r and n?
Yes. So we are looking at a point inside the outer cylinder and outside the inner cylinder. Because everywhere else, either E is 0 or B is 0. And then we said, okay, so this is what we have for the pointing vector. If we divide this by 1 over c squared, we get the linear momentum density. And you see that the linear momentum density is in the minus phi hat direction. So basically, linear momentum vectors just circle around the z-axis in the clockwise sense. And so you would expect an angular momentum corresponding to this electromagnetic radiation in the minus z hat direction. So let's calculate the angular momentum per unit length divided per unit length. This will be equal to r cross s over c squared integrated in my volume times 1 over L. It's just r cross p. P is now the density, so we have to s over c squared is the momentum density. So if you just imagine a volume dv, that volume has the momentum s over c squared times dv. R cross p, you just summed over all volumes. So this will be equal to 1 over L. Well, we have an integral over z, let's say from 0 to L per unit length. So we take a length L of my cylinder and calculate the total angular momentum within this length L and divide by the length L to calculate the angular momentum per unit length of my system. Then I have an integral over phi from 0 to 2 pi, and then an integral over s from A to R, because this is the only region where I have some linear momentum. Outside this range of s, my linear momentum is 0. R cross s over c squared is, R is s in the s hat direction, plus z in the z hat direction, cross, well, let me move the c squared out. S is a sigma I n over s in the minus phi hat direction. So this is equal to a sigma I n over c squared. Well, there's nothing that, well, something might depend on z. So let's just say L from 0 to L dz, from 0 to 2 pi d phi, from A to R s ds, s times s hat cross phi hat, you see if you have this circular coordinates at this point, this is our s hat, z is outside, this is our phi hat. So s cross phi hat, s hat cross phi hat is plus z hat. Well, we have the minus, so it is the minus z hat. And plus z times z hat cross phi hat minus s hat. Well, I have the minus over there also, s hat. Over, no, this s cancel, this s. Now basically this is all I have. But keep in mind, the integral over phi of s hat, this is equal to 0. From 0 to 2 pi. Why? Basically because from 0 to 2 pi d phi, s hat is nothing but cosine phi in the x hat plus sine phi in the y hat. The integral of both cosine phi and sine phi over one period is 0. So we get the angular momentum per unit length is a sigma I n over c squared L from 0 to L dz, from 0 to 2 pi d phi, from A to R ds times s in the minus z hat direction. Well, nothing depends on z now, so the z integral just gives me an L, a factor of L, which cancels the L in the numerator. So I have a sigma I n over c squared times minus z hat. The phi integral just gives me 2 pi. And the s integral gives me r squared minus a squared over 2. 2's cancel. So I'm left with a sigma I n pi over c squared times r squared minus a squared in the minus z hat direction. Now this is kind of what we expected, in the sense that the linear momentum density is circulating around the z in the clockwise sense. So we expected to have an angular momentum in the minus z hat direction, and this is what we obtained, that r squared minus a squared is a positive number. Then we said, okay, this is the I, this is the charge density sigma. We said, okay, let's turn off this I. There will be an induced electric field. And the induced electric field, there will be an induced electric field at the position of the inner cylinder, which has a charge. Well, the electric field, the induced electric field will be in which direction? I'm reducing I. I'm reducing I, so it is counterclockwise or clockwise. So I'm reducing I, so it will be counterclockwise. Okay. So basically this will be the direction of the E field. And we can determine the magnitude of this E field by just using E dot dl is equal to minus d phi b by dt. E dot dl around this loop will be E times 2 pi s minus d by dt. The flux is B, whose magnitude we had calculated, 4 pi I over Cn. times the area is pi s squared. Only I is changing, so E is will be equal to, let's cancel these 2 pi's, 2 left over here, s cancels one of this, minus 2 pi s n over c di by dt. Well, we already know the direction, so this is the magnitude. Ignore the minus sign. Or let's say, let's not ignore it, because di by dt is negative in our case. Well, this will create a torque on the inner cylinder. You see the torque is R cross F. So I have this inner cylinder. At this point, let's assume I have a patch over there with area dA. So the total charge is sigma times dA. There will be a torque acting on this patch. Well, this is R. My F is in this direction, or let's say dF is in that direction. So R cross dF is in which direction? Z direction. So this is definitely in the Z direction. And its magnitude is just, since the two vectors are perpendicular to each other, it's just F times A. A is the distance. Magnitude of R is A. So this is equal to, in the Z direction, or let's say dF. Now dF is E, which is minus 2 pi s n over c di by dt, times dq, which is dA, times, okay, some bad notation, let me just change this to s, times A. A I use for the distance. Well, if you just integrate it, the torque acting on my system is just in the z hat direction, minus 2 pi s n over c a times di by dt, the total torque per unit length, let's say. The only thing that depends on my patch is ds. I'm just summing over the patch, the ds, the areas of the patches. So the total area of a length L is just 2 pi A times L over L. So they cancel. It's just 2 pi A. This is my torque. Torque per unit length. This is equal to Z hat minus 4 pi. Now this S is also A, because I'm looking at a distance A. 4 pi A cubed n over c times di by dt. But you see, torque is nothing but d by dt of the angular momentum, this time per unit length, of the, let's say, the inner cylinder. Let me just call it A. You just integrate it from t equals 0 to t equal infinity, let's say. At t equal to 0, you have this total current. At infinity, the current is 0. And you get LA final over L. Initially, the inner cylinder is at rest. This should be equal to minus 4 pi A cubed n over c in the z hat direction, I final minus I 0, which is equal to 4 pi I A cubed n over c in the z hat direction. So this is the final angular momentum of the inner cylinder. Well, you see, we have a problem here that we need to address. Initially, we have the angular momentum per unit length of the electromagnetic field. It was in the minus z hat direction. And since my inner cylinder was not rotating, there is no angular momentum there. This was the total angular momentum of my system initially. And now I have this angular momentum. Sorry, I forgot some factors. dF is E. There's a sigma over here. E is A sigma over S. Hold on. No. The induced electric field is, now let me just make this correct. The induced electric field is A sigma over S. So here I need to have the induced electric field in dF. No, this is the induced electric field, sorry. So here there is sigma. In the B field there's a, no, there's no sigma. There is a sigma because of the, in dq there is a sigma. Yes. So this is over here, dF is nothing but E times dq. E is 2 pi a n over c di by dt, dq is sigma ds. So here there is a sigma.
Is that Q at the end of? Is that Q or A?
This one.
Yes.
This is A. You see, it is this A. A is the length of this R vector. Now let's see if there are any other mistakes in our derivation. Well, there's one more problem with the factors of C, but we will come back to that later on. We have some other problems that we need to fix. Now, definitely there's a, besides the factors of C and some pi, some numerical factors, we can check it again. There's another problem. The initial angular momentum, as I said, was in the minus z direction. But the final angular momentum, at least within this limit, is in the plus z direction. So apparently there seems to be a non-conservation of angular momentum. Yeah, that is kind of a problem. But just note one thing. This is equal to A sigma I n pi over c squared r squared in the minus z hat direction plus A cubed sigma I n pi over c squared in the plus z direction. Look at the second thing and compare it with the final angular momentum of my inner ring. One thing is there is a mismatch of units, and that is from here, this is 1 over c. So we have this additional factor of c squared. Now, besides this factor 4 over there, which we will check in a moment, they're identical. So if it wasn't for the first term, then we could say, okay, the angular momentum is conserved. Now let's find that factor 4 also. Let's correct that factor 4 either in our initial derivation or this final derivation, and then we can discuss what's going on. So let's look at the first derivation. Here we have C over 4 pi. We calculated the electric field. And we know the magnetic field. So 4 pi over C is cancel. Okay, this is our S. So we are calculating R cross S. So that term is 0. And then we have here the 2 pi cancels. Well, this seems to be the correct answer. Let's look at the induced electric field case. Now the induced, the area is 2 pi a times height L. We divide by L. So there we have a 2 pi a. In the electric field, we have a 2 pi in the... So is this correct? So the electric field times E dot dl is E times 2 pi S is minus d by dt. Phi b, the B field is 4 pi over C I times N. And the area is pi S squared. Well, okay. I don't see that factor 4. But let's keep it and then we will see what's happening. Well, there are basically a couple of issues that we didn't really take into account. Now, one problem is, okay, we always say that, okay, outside the magnetic field is 0, well, which is basically an approximation. So if you have a finite solenoid, it won't be 0 outside. And even in the ideal case, well, outside is 0, nevertheless, it creates an electric field. So it does have non-trivial effects outside my solenoid. So there might be some magnetic field, some effect of the magnetic fields. Of course, we can take the limit of real solenoid, send the length to infinity. But you see, if you take a real solenoid outside, then there will be some magnetic field outside. There's already an electric field outside. The electric field decays as 1 over the distance. And there's a magnetic field, let's say, if it decays as 1 over the distance squared, the pointing vector will have this 1 over distance cubed behavior. Its volume integral diverges. So outside there is an electric, there is a linear momentum, at least. Well, in the solenoid will be a dipole, so it won't have this 1 over s squared behavior outside. It will have more like 1 over s cubed, at least if we are very far away from the solenoid, it will have this 1 over s cubed behavior. Then the electric field has this 1 over s behavior. So let me write it this way. Let us take this finite size solenoid. Inside we have this cylinder. Very far away, the B field behaves as 1 over r cubed. The electric field behaves as 1 over r squared, very far away. Because very far away, this inner cylinder will just look like a point. That is why it is not even squared. It's not even 1 over s, 1 over r, it's 1 over r squared. Very nearby, it has this 1 over s behavior, but very far away, it will have this 1 over r squared behavior. So s behaves like 1 over r to the 5. R cross S behaves like 1 over r to the 4. L, which is the integral of r cross S over the whole volume, behaves like dr over r. because dV behaves like the volume in, no, sorry. It goes as dr over r squared. Well, which is not so small. Okay, it converges, that's something nice, but it's not so small. On the other extreme, we can say that, okay, this is the behavior at the faraway point. Now, if you are very sufficiently close to the solenoid, well, E field behaves like 1 over r. Let's assume B field still behaves as 1 over r cubed. Then S behaves as 1 over r to the 4. And the L behaves as the integral dr over r. This is large, not necessarily small. Now, the lesson is that maybe the total angular momentum outside is not so small, which we completely ignored. Well, we can make it smaller.
Hocam şu bence insanların integral var mı yok?
There's an integral over there.
O zaman diğer uğrağı olur mu?
No. You see, r cross s is 1 over r squared. dv has r squared dr. And I also have that 1 over r to the 4, so that's fine. Well, the problem is, okay, the magnetic field outside can be negligible, but outside the solenoid is huge, infinitely large. So it's kind of 0 times infinity uncertainty. It need not be negligible. But we can make it negligible by, this is our solenoid. I have this sigma over here. Let me put another cylinder outside, which has charge minus sigma prime. Well, I will choose the other sigma prime such that sigma times A, let me call, okay, this is A, let's call this B. Sigma times A is equal to sigma prime times B. So that outside electric field is 0. Here E is equal to 0. Inside, nothing really changes. Well, since the outside the electric field is 0, well, the S pointing vector is E cross B. B, we said it's 0, but maybe not negligible. Well, maybe since it's an infinite volume, it might give a finite contribution. But now E is also almost negligible outside. So essentially, it's double negligible, let's say. So it's double 0 multiplied by infinity. Kind of hopefully it will turn out to be 0. But if we put this additional cylinder outside, there is an EMF acting on that one also. And hence the outer cylinder will also acquire an angular momentum. So we have to take into account the angular momentum acquired by the outer cylinder. Now, what is the direction of the electric field outside? Sorry, the induced electric field, yes, as I is decreasing. Well, let's say I is decreasing. So outside, counterclockwise or clockwise? Clockwise. It's also clockwise. Do you agree? You see, what does the Lenz's rule say? It says that if there are induced charges in the system, the induced charges will be such that they will try to resist the change that creates it. So what is the change that is creating this induced electric field in terms of the flux? It's the reduction of the flux. B field is initially out of the screen. So its magnitude gets smaller. That is what will be creating the induced electric field. So the induced current should be such that it will create an additional B field. So the induced current should create a B field out of the screen. But that tells me that the induced electric field should be in this direction, also outside. Yes, the induced electric field is counterclockwise. Both inside and outside, the induced electric field is counterclockwise. But you see, on the outside, the charge is negative. So the inner cylinder, it rotates clockwise. Now the inner cylinder will rotate counterclockwise. The outer cylinder will rotate clockwise, because its charge is negative. So hopefully that will give us an additional angular momentum, which will balance our imbalance in angular momentum conservation. So let's see, what is this induced electric field outside? E induced times 2 pi s, this is E dot dl. This should be equal to minus 1 over c d by dt, b times pi r squared. Well, b is 4 pi over c. No, b is 4 pi over c I times n. So this is equal to 2 pi cancels the 2 over here, and we end up having E induced minus pi 2 pi r squared I n over c squared, no, not I, s di by dt. This is the induced electric field. Again, we will do the same thing. We take some patch over here, ds. It has a charge dq. So dq is equal to minus sigma prime times ds. The force acting on it will be minus 2 pi r squared n over c squared s di by dt times minus sigma prime ds. This is the force acting on it. So the torque will be 2 pi r squared n over c squared. Well, the s is on the outer cylinder, it's b times di by dt times sigma prime, so this is d tau, times b. B is the magnitude of the distance. So B's cancel. So we get 2 pi r squared n over c squared. There's ds, di by dt times ds. This is the tau. The total tau will be 2 pi r squared n over c squared di by dt, torque per unit length, 2 pi b. Sigma prime. Just integrate it from t equal to 0 to t equal to final. So this will be L, B, let's say, final per unit length is 2 pi r squared n over c squared. 2 pi b sigma prime times minus I. I final is 0, I initial is I. Okay, so where are my mistakes? Which one? This one. We see torque is equal to R cross F. Magnitude of R is equal to B. So let me check a couple of things. 2 pi s n over c squared. Okay, so these are the same. So what happened to this pi over here? Nothing. So that's pi squared, right? So this is pi squared, this is pi squared. So this is in the, let's say, minus z hat direction. So let me just, this is 4 pi squared r squared and b over c squared sigma prime I in the minus z hat direction, or 4 pi squared r squared and a times sigma over c squared I in the minus z hat direction. Now let me take the other term I had, both of which likely contain the same error. So this was LA. So this is pi squared. So if you just sum them up, LA plus LB, final per unit length, is 4 pi squared A sigma over C squared times R squared minus A squared times N in the minus z hat direction. Now let's compare this with the angular momentum of the electromagnetic field. Let me write this in this form, 4 pi times pi. There's an I. Besides this factor 4 pi, they are equal now. So you see, furthermore, we know that sigma times A should be equal to sigma prime times B. So in principle, this outer cylinder, we can just put it very far away. So B is very large, but then sigma prime will be negligible. So actually there we can even set it to infinity. We put zero charge at infinity, but nevertheless its contribution to the angular momentum conservation just turns out to be finite. Like 0 times infinity uncertainty. Let's find what this 4 pi comes from. Where was our mistake? Either we forgot the 4 pi in the electromagnetic case, or we have an additional 4 pi in the calculation of the angular momentum transferred to our cylinders. In S, do we have this 1 over 4 pi? Or let's see, let me look at this one. Here is where comes the 4 pi. What is curl of B? Or what is B dot dl? Is there a 4 pi? Yeah, there's a 4 pi. Let's see, what about E? Which E? The induced one or the existing one? This one. Well, what do we know? E dot dl, E dot ds should be equal to 4 pi times Q enclosed. So here I have a 4 pi. So basically I forgot a factor of 4 pi in the electric field, so hence in the expression of S. Okay. So we have the conservation of angular momentum in this problem, done properly. Let's give a 5-minute break, and then we can continue.